This one should go pretty quick. We've done this problem a long time ago. They give us a velocity equation and then they say, what's the integral of that velocity? So your number one representation of your integral is the area. So you're going to find the area of this trapezoid right here. Now, you could draw in a couple lines here. You could do a triangle, a rectangle, another triangle. You're gonna need to know the area formula for a trapezoid anyways, because sometimes I'll have us either use rectangles or trapezoids to approximate our integral and use that sum. So on the back of the second page in your blue packets, I have the area for a trapezoid formula for you. We need to know that. And then so I just did base 1 plus base 2 divided by 2 times it by the height. This is a no calculator problem there, so you just got to make sure you could do that in your head without the calculator. I like to do 20 divided by 2 first to get to 10, and it's easy to times that by the 36. Now, whenever you integrate velocity, that's going to give us position, right? So if you integrate meters per second, how fast you're going, that's going to give you the position, which is just going to be meters. And so that helps me interpret my answer right there. So I got 360 meters. And then when you interpret your meaning, you got to just mention the car travels 360 meters, but put in 0 to 24 seconds. All right, put in 24 seconds because you got, if there are numbers attached to that integral, you have to be specific and you got to make sure you mention those numbers right there. All right, now for letter B, it says v prime of 4, v prime of 20. We know that's a derivative. We know the number representation of the derivative is going to be the slope. Now at x equals 4, at t equals 4, there's a corner point right there. So we put v prime of 4 does not exist. And the reason we always use for that is multiple tangent lines. Now when it says v prime of 20, that's the slope at x equals 20. So at x equals 20 is right here. That's that one dot right there. That's a line segment. So you just got to find the slope of that line segment. So I wrote down this point was 24, 0. This point is 16, 20. So all I'm using there is just my slope formula. Y is on the top, subtract the x's on the bottom. You get your slope. And then if you're doing the derivative of velocity, that's going to give us like an acceleration. So the units for acceleration are always like those weird meters per second squared type of units right there. So the normal position would be meters. The velocity would be meters per second. The acceleration, which is the derivative of that velocity, is going to be meters per second squared. It does say indicate units of measure, so we need that. But so far, all we did on this, we did derivative with slope. We did integral with area. That'll get you through tons of this AP test right there. Letter C is asking for the acceleration. So how do we get from the velocity that they gave us to acceleration? To get from velocity to acceleration, we know we're supposed to take the derivative. And this is why they're requesting a piecewise function, because there are 3 different segments of this graph, which means there are 3 different slopes. But all this is just 3 different slopes right there. So I did in between 0 and 4, 4 and 16, 16 and 24. I didn't include bars underneath theirs because those are the endpoints and the corner points, and the graphs are not differentiable at the endpoints and the corner points. So the derivatives don't exist. And that's what this is. This is the derivative equation of that velocity graph right there. So just right here, you could write down the points, do your slope formula, or you could just count rise over run. We went up 20 over 4, so that slope is 5. This is horizontal, so that slope is 0. This, we went down 24 to the right 8. So if you reduce that fraction, or actually we already found that slope in part B, or already did that one, that's a -5/2 right there. And that's just 3 different slopes, 3 different derivatives there. All right, so part A through C, we'll have down with just effort and exposure to a bunch of these kinds of problems. Letter D says find the average rate of change. Now, when you get stuck on something, I encourage you to continue to keep looking through your blue packets. On the second page of your blue packet, it says average rate of change, and that's just your slope formula. So the first part of that, when it says find the average rate of change between 8 and 20, I just did my slope formula. I did v of 20 minus v of 8 over 20 minus 8, and I'm using my slope formula. And so those we're getting from the graph. So at the 20 and the 8, those are going to look at there and say, what is that y value? At the 8, what is that y value? And then that's where I'm getting the 10 and the 20 from right there. And then subtract those, you're going to get that -5 over 6. This one didn't specify units, so I guess I wouldn't have needed to include those. But since you're doing the slope of velocity, we know that's going to be like a derivative of the velocity, which is like the acceleration. So the units would be acceleration right there. Now, for the last part of this, it says, does the mean value theorem guarantee a spot such that the derivative is equal to the average rate of change? If you need help with the theorems, I have the separate video created, just me reteaching the theorems, where you can go and look at those if you need to. The 4 big ones that we got to know are on our blue sheet right here on our blue packet. And so when it says mean value theorem, they all have that continuous and differentiable talk there. But if you have a continuous and differentiable curve, it guarantees a spot where that derivative is equal to that average rate of change. And I actually wrote that down again right here, right? If you have a continuous and differentiable function, the derivative is equal to that average rate of change. This one isn't even having us apply the mean value theorem. It just wants to know, does the mean value theorem apply? So usually for a theorem to apply, it's got to be smooth and curvy. It's got to be continuous. It's got to be differentiable. Now, this particular graph is continuous. I don't have to lift up my pen when I'm drawing that whole graph there. So it's continuous, but it's not differentiable at those corner points. So it says in between 8 and 20 only. And so in between 8 and 20, right there at the 16, I put no, this theorem doesn't apply since the V is not differentiable at t equals 16. But if you haven't already, check out that video I created where I retaught those theorems that I just went through quickly, each one real quick, and then we'll go through, I'll keep reteaching those as we go through these extra videos for how to do the problems right there. Avocado.